Okay, good morning everyone. So I'm Isak Engquist, senior scientist at LUE. Been working here for a bit more than 10 years. And I'm going to give you a bit more of background into what Magnus already introduced, the wood or paper batteries, as we usually call them, and supercapacitors, which is the more appropriate name maybe for what they actually are. First, just a few words about the printed and paper electronics group, for which I am the manager. We have, as Magnus explained, 10 different subgroups at LUE. This is one of them. We do printed electronics, electronic circuits on plastic or on paper. We do paper electronics, which is electronics in paper. And of course, we also try to combine it. So we want to print the paper electronics. And that's one of the things I'm going to tell you a bit more about. Right now, the scientific people of the group are these. Some of them are here. And you're very much welcome to talk to any of them, of course, also about what they do in particular. I'm going to talk about energy and problems with energy that we have today. When we go to more and more renewable energy sources, we will have a need to intermediately store energy more and more, because wind and solar power are not delivering power like this. It's constantly going up and down because of clouds, because of daylight and night and so on. And a large portion of the energy production in the world needs this kind of intermediate storage. And you can try to imagine how many % of the production we need to store in that way. I'll give you 3 seconds to think, and then I'm going to tell you that it's about 1/3 of all the energy. Think about that. All the energy in the world, 1/3. How are we going to store that? And as I said, the basis for this is, for example, wind and solar power. Over a month, the production can look like this. Over a day, it can look like that. That's why we need it on the scale of minutes to hours to store energy intermediately. So, how do we store it? There are different ways to store it. Electrical energy typically is stored in batteries. We all know that. So something like batteries, yes, maybe that could be a good idea. So let me tell you about electronic components that can store energy. There are capacitors, supercapacitors, and batteries. And just so you know the basic definitions of these, I'm going to tell you briefly about this. This is a capacitor. It has 2 electrodes, typically metal, and between them there is a dielectric material. If you apply a voltage, this dielectric material can polarize. That means small dipoles in the material will arrange, and in that process energy is stored. Then there are supercapacitors. They also work by rearrangement of charges, but here you have, between the 2 electrodes, you have an electrolyte with positive and negative charges, ions, that can move around. And when you apply a voltage, positive ions will go to one electrode and negative ions will go to another one. That principle will give you the ability to store more energy. But in order to store even more energy, what you do is that you structure the electrodes so that they have a much larger surface area. And then all that surface area becomes available to store the charges. And then you have what you call a supercapacitor. Then there is a variation where also you allow the charges to actually go into the electrode material a bit. That's a supercapacitor. In a battery, this is the school example of a battery with has 2 metal electrodes in a liquid electrolyte. In a battery you have electrochemical reaction at both the electrodes, so that here, for example, zinc is converted into zinc ions in the electrolyte and back again depending on its charging or discharging. So here, charges are not only moved, they also actually react with the electrodes. So that's the difference between capacitors, supercapacitors, and batteries. And these things also give properties. They are differently good at different things, these components. And usually you show this in a so-called Ragon plot, where on this axis you have, let's start with this one. On this axis you have energy. So if you have 1 kilo of this component, how much energy can you actually put into it in, for example, watt hours or kilowatt hours? Up here is more energy per kilogram. And then it's a question of how fast can you deliver the energy out or charge it again, in and out. How fast can you do this? That's power. And that you have here, power per kilogram, more power to the right. So obviously this upper right corner is the best corner. You would like to be here with all the components, but in the real world it doesn't work like that. Different components are good at different things. And as you see, batteries have a lot of energy, but they are not so fast in charging and discharging. Capacitors are very fast charging and discharging, and supercapacitors are somewhere in between. So in a way, it's actually the best of two worlds. And that's one of the reasons why we aim for supercapacitors. Just to give you an example, this ordinary type of AA battery that everyone has at home lands around here. It has a lot of energy density, but not so fast. Okay. How do we make supercapacitors? Because that's what we try to do here. Well, we take nanocellulose, nanofibrillated cellulose, mix it with the conducting polymer P.PSS, blend it, and we get this power paper, which actually is a paper, although it's black. The interior structure, as Magnus already shows, is something like this. You have the fibers of cellulose, and they are covered with this conducting polymer. So that gives us a possibility to make a wood-based supercapacitor. You remember, a supercapacitor needed a lot of area here. That's the key to a supercapacitor. Well, this is nanocellulose. It has a huge surface area. So if we make it conductive with P dot, you get a perfect electrode for a supercapacitor. And that's why cellulose is so good and so important. It gives you both the structure, the mechanical stability, and it gives you this huge surface area. So here is how you can make a supercapacitor. You take this P dot cellulose paper, you add a few layers to add the current to it and the electrolyte, and then you make this all over again as the second electrode, and you laminate those two together. And you can do this in a printing machine. This is how it looks printed. It's mostly black. This is when it's laminated together. These are test cells that we do in our lab here together with rice. And I'm going to let Jesper Edberg, who used to be a PhD student here, who now works at RISE with these things, give you a demonstration of what these components look like and how they work, hopefully. So Jesper, I will show the movie of how this process is going, and maybe you can come forward and bring the things while I show the movie. So this is, I wonder if I can get it started. Yes. This is a cartoon of how we make it. We mix P dot and cellulose. We start with actually the DPP processed electrodes that Magnus was talking about before, aluminum. We cover it with carbon in a printing process. We add the P dot cellulose, and now we have the electrodes, one electrode for the supercapacitor. And then you make another one and you laminate them together, pressing, and that's when you have a supercapacitor that can store energy. In reality, it looks like this. You can actually fold it together. It's soft so that it has a nice possibility to be folded in different ways. You can make it like that, and it's kind of small. And you can envision different ways of using it. You can power different things with a small package like that. You can use several of them to power a bit bigger things, like small electrical motors, for example. Or you can do what is really our main vision, pack a lot of them together, container size, and use them for intermediate energy storage. That's the vision, that's what we are aiming for, and we have already come quite far. And Jesper, please, if you can show how it works.
So I'm very glad that Magnus showed this video in the beginning where you actually saw the supercapacitors working. I realized today that our freshly made supercapacitors are actually out traveling, so I only found an old one. We'll see how it goes. But to begin with, I think you've seen this quite a few pictures now. This is the basic component of the supercapacitors. It's power paper. It's electrically conductive paper that can also store energy. So it's actually inside of these supercapacitors here. This one is also quite old. It doesn't look so good anymore, and I blame Peter Wallenberg for this. Actually, he was quite rough on this one when he signed it. And I think I will send this around. I think you can still see his thumb imprint in the middle there.
And we have to say that the paper industry has spent 100 years to make paper white, so we make it black.
So, what I'm actually doing now is I'm charging up the supercapacitors, and then we will see if I can actually power this fan with them. Usually I have to charge it quite a lot in the beginning, and that's because a supercapacitor works a bit differently from a battery. A battery have a constant voltage output, while supercapacitor the voltage falls as you start using it. So first have to charge it up quite a lot, and then you use the top of the power. Let's see how this goes. Okay, we have some spinning. Now let's see if I can charge that again.
So you are actually simulating the wind power plant at this stage.
No, it's manpower. But the power is locally stored in the supercapacitors, and then we can utilize it. So yeah, it's not a lot of power right now. I blame supercapacitors being quite old, but you saw in the video that they can work a lot better.
Thank you, Jesper.